Linearity versus non-linearity. In the last lecture, when we discussed about activation functions, we said that activation functions introduce non-linearity into neural networks. Automatically, the next question that will come to your mind is what exactly is this non-linearity? We already discussed basics of non-linearity in the last lecture, but here we are going to dive a bit deep and understand what exactly is linearity and what exactly is non-linearity. The reason we are having this lecture here is having this clarity will help you in all the upcoming lectures as well, where we are going to discuss about more activation functions, and this clarity on linearity and non-linearity will help you. Let us understand in detail what is linear and what is non-linear. First thing is what is linearity. Before getting into all the technical jargon, let us understand in simple layman terms. That is, if you have a relationship between x and y, this can be called as linear if it is simple and predictable. This is the basic way in which you can say it is linear. If simple and predictable relationship is linear, then what is non-linear? If this is simple and predictable, then the opposite of it, non-linear, should be complex and unpredictable. Let us take one example scenario and understand when it is simple and predictable and when it is complex and unpredictable. Let us say you went to buy a toffee and you know that you will get one toffee for 1 rupee. If this is the scenario, if you want 100 toffees, how much money would you want? You will want 100 rupees. The same way, if you want 1000 toffees, then you will need 1000 rupees. This is a linear relationship. This is a simple and predictable relationship. That is, if someone tells you one toffee costs 1 rupee, you can easily find out what is the cost of any number of toffees because it is linearly scaling. Next thing, let us take another example, an example of a non-linear relationship. Let us say you want to invest in stock market. Okay, you are investing some money, 1000 rupees in stock market. At the end of first year, let us say you got 1500 rupees in total. That is, your 1000 became 1500. But at the end of second year, it decreased value and reached 1400. And maybe at the end of third year, it again shot up and reached 2100. So this relationship, this is not linear. This is unpredictable. Looking at this value and this value, it is difficult for you to say what is this. So this is complex plus unpredictable, which means this is a non-linear relationship. I gave a basic idea here and a basic example so that you get first overview of what can be called as linear and what can be called as non-linear. Now let us get into the technical terms and understand what exactly is linear. In machine learning, what things do we consider as linear and how to identify it is linear or non-linear, or when do you want activation functions to be used. Okay. Again, we'll take the same example. Strictly going by linear algebra, strictly if it has to be linear, it has to follow two properties. First property is called as the property of additivity and second property is called the property of homogeneity. So this is the strict definition that we are going through. Additivity says if you have a function and f of x1 plus x2, if this is same as f of x1 plus f of x2, then it is told to follow additivity property. So this is the first condition. Second condition, which is homogeneity property, it says that if a is a scalar value, then f of ax, this should be same as a into f of x. These two properties, if both of these are followed, then it is a linear relationship. But let us just see a basic example and then understand something more. According to these properties, if you have something like this, f of x is equal to 5x. If this is the equation you are having, this is the function you are having, do you think this is linear? According to these definitions, is this linear? Because if you have f of x1 plus x2, that will be 5 into x1 plus x2. Is this same as f of x1 plus f of x2? If you do f of x1 plus f of x2 separately, you will have 5x1 plus 5x2. So here you can see that this is same as this. Now I'll give you one more example and then you have to tell me whether it is linear according to you or not. Okay. So the same function f of x, if you do it 5x plus 1, if it is 5x plus 1, then what happens? Do you think it will still follow this additivity property? If I do f of x1 plus x2, then it will be 5 into x1 plus x2 plus 1. But if I do this f of x1 plus f of x2, then it will be 5x1 plus 1, this is f of x1, plus f of x2 will be 5x2 plus 1. So this will give me 5x1 plus 5x2 plus 1 plus 1, which is 2. So here additivity property is actually violated. So according to the rule, that is according to this rule which says both additivity and homogeneity has to be satisfied for it to be linear, then by that rule f of x equal to 5x plus 1 is not linear. But in machine learning, whenever we are considering these things, we are not going to go by this strict linear algebra definition. Instead, the affine functions are also coming under linear. So affine means a linear transformation along with a change in its position. That is, if you simply have 5x, then it can only change in this. That is, this is 5x. It can be 10x, something like that. But instead, if you have the affine transformation, instead of y is equal to mx, you will have an option of having y equal to mx plus c. That is, this line when shifted by c becomes y equal to mx plus c. Graphically, if you see, it is something like this. If you have a graph here, then let us say if y equal to 5x or y equal to 2x, something, it goes something like this. If this is the scenario, this is your x-axis, this is your y-axis. If you shift this line to somewhere like this, then it is an affine transformation. So all the affine ones are also considered under linearity. So in machine learning, generally when you are saying it is linear, your neural network, it is able to see only linear functions. Then you can see somewhat like anything that draws a straight line, or you can say any of the affine transformations, all those are coming under linearity. So these properties of additivity and homogeneity, you don't have to strictly follow. Instead, if you are able to follow anything which does not go for curves or bends, then it can be considered as linear under the scenario. So any of these functions, something like, let us say 5x plus 7, or maybe x1 plus 2x2 plus 3, all these sort of functions are considered as linear functions for all our purposes. So this is where or the example that we considered initially, something like if you get one toffee for 1 rupee, then 100 toffee for what money? Or let us say if someone borrowed 100 rupees from you under a condition that they'll give back 5% additionally. So instead of 100, if they took 200 rupees per you, still the relationship will be linear, right? These are the linear relationship. So classic equation in order to represent these will be y is equal to mx plus c. So this is the equation of a line where m is the slope of the line and c is the y-intercept. What is meant by y-intercept? When you have a graph like this is your x-axis, this is your y-axis. Wherever your line meets the y-axis, that is called as y-intercept. And what is the slope? Slope decides this, what is the slope of this line. This is called as slope. So now you understood a basic idea you got about what is linear. Next question is, what is not linear? What is not linear or non-linear? Coming to non-linear, again, you can say this is a complex or unpredictable scenario. Whenever you want to model something complex, you always need a non-linear relationship. So this is where activation functions comes handy, because without activation function, you will only be able to model linear relationships. But when activation functions comes in neural networks, this is when you will be good enough to handle any of the non-linear relationships, and that is when complex functions can be handled. So here some examples can be something like f of x is equal to x square. So this is not a linear relationship. It is x is getting squared, which means if you give 1, it will stay as 1. If it is 2, it becomes 4. If it is 3, it becomes 9, and so on. So this is a non-linear relationship. Or let us say something like f of x is equal to sin x or cos x. All these are non-linear relationship. Or f of x equal to e power x. These are all, this is exponential. All these are non-linear relationship. Another way of understanding this is, instead of a straight line, this time it can bend, it can curve, it can make any sort of complex designs or complex relationships can be shown using this. Next question is, how is this important in a neural network? So how is it going to affect your neural network? This is what we have to understand. In order to understand that, we will take a basic equation here. Let us say something like y equal to w1x plus b. Something like this, let us say, is your equation. If you have something like w2, let us say I'm writing as w2 into w1x plus b plus b2. If I have something like this, is this linear or non-linear? This is straightforward linear. If I have this as the scenario, then what do you think? I want to show you where activation function comes in. Okay, I'm taking a simple neural network. In one neuron, what happens I'm showing you. Then I want to show you what happens when this activation function comes into the scenario. Okay, so if this is my neuron, in that neuron initially I was simply having a linear transformation, which is w1x plus b. That is, x is my input, w1 is the weight in that neuron, b is the bias. Then when given input x, it will make the transformation w1x plus b, which is linear. Instead, if I make this transformation w2 into w1x plus b plus b2, then still I can expand it as w2 w1x plus w2b plus b2. So this is still a linear function. So it is still a linear transformation. I want to show you when it becomes non-linear. So you can see that even in this, there is no activation function used. So what is the situation here? I told you in previous lecture that when you stack up different layers, but all these layers are linear, then even if you pass through all the layers, it will still remain as linear. That is what I had shown here. That is, let us say after one layer you have this as output. Let us say at the end of this layer you got w1x plus b. You are giving this output to the next layer. Then what happened? It did w2 into input from first layer plus b2. But still this is a linear relationship only. So like this, even if you stack 100 layers, still final model will simply be a linear model. This is what I want to tell you. So instead of this, I want to show you what happens if you had add an activation function in each layer. So instead of this simple w2 into w1x plus b plus b2, if I had an activation function f in the second layer, then what will happen? It will be w2 into, after the first layer, this will go through an activation function. Then the output will be f of w1x plus b, then plus b2. So after I have this w1x plus b, it will go through the activation function. It will become f of w1x plus b. And then when it passes through next layer, w2 will be multiplied to this final output and plus the bias of the second layer. But this time you won't be able to write it like this because you have this activation function here which is adding a non-linear transformation. So this is no more a linear relationship. It is a non-linear function now. So this is how introduction of activation function into the layer changed it from being a linear transformation into a non-linear transformation. So this is what I want you to understand. That is when you added the activation function, how it changed from a linear situation to a non-linear situation. Now in the coming lectures, when we learn exactly what this function should be, then the whole picture will be clear. So what we are going to discuss in the coming lectures is what are different activation functions and what exactly do each of those activation functions do. When you understand that, then this whole picture will be very clear of what particular non-linear activation is done here and why is this whole thing not linear. Okay, so in the next lecture we'll go to activation function, the first activation function that we have to learn.